Okay, so plan for today is to talk about permutation tests. So wrap up the material in chapter 3. So last time we were kind of focusing on how we state the hypotheses, kind of informally, what we're looking for significance, and kind of how we can measure that significance with a p-value. And so the example we did last class, kind of the hypotheses. So this was like the do I have telepathy example. In that case, that process was like a binomial distribution. So we were able to come up with like, if the null hypothesis is true, this is how we would expect things to be distributed. And we were able to calculate a p-value from that. In many situations, when we're comparing two groups to each other, we actually don't have enough information claimed about the underlying distribution. So we can talk about another way of finding these p-values, running simulations, and doing permutation tests. So the reading quiz went through more with this. Well, the video went through more with the unscrupulous diner example. So were there any questions about how we counted up those total possibilities, got the test statistic? Okay, and so then we'll kind of get into the permutation test process then today. We can kind of go through some examples with this. And kind of the point I want to make over here is, if we did this experiment and we found like a difference of $2.56, the question is, right, is this difference due to behavior of people that they order more when they're over here as opposed to over here, or is this just due to the randomness of how people were split up? And so that's where these permutation distributions come from. We can take a look at what are all of the possible ways that we could have divided these people up. Out of all of those ways, right, we found like that there were 7 just or as extreme or more extreme. So that gave us a p-value of 7 out of 70. And then we got to make sense of that 0.1, right? The idea here is it's telling me if there really was no difference between ordering preferences, then there would be a 10% chance that we would have observed a difference as large as the one that we did. And then we can argue about whether 10% is a lot or a little. Probably it falls somewhere in the difficult realm of like, that doesn't sound all that likely, but it's not that unlikely either. Okay, and then for the example that you guys had to look at for the quiz, dealt with this data set called beer wings. So this was one of the data sets in the resampling resample data package. And so here, the researchers were kind of interested. The researchers, they were students that collected this data, were interested in whether males or females order more hot wings at a bar. I don't know, that was their research. And so they went out, they picked a sample of males and they looked at how many wings they consumed, females. And if they're trying to determine whether males eat more hot wings than women, right, then we could state these hypotheses in the following way. So one would be, we think that this difference is going to be 0, where these mu's, right, refer to the means of all men who eat hot wings, all women who eat hot wings. And the alternative is, well, they suspect men eat more. So that's why we have a greater than sign over here. And then we could go ahead and calculate the test statistics. So I could add up all of these values over here, take their average, and that comes out to 14.53. We can calculate these in R in a moment. And then we go over to all of the females, 15 females, their average was 9.33. So that's a difference of, a little over 5 wings. And then we can ask, is that a reasonable difference, or is that seem like it is significant? And so now if we want to consider the permutation distribution for this, we have 30 people in the study, right? 15 of them are male, 15 of them are female. So we actually have two even-sized groups here. So if you did this one on the quiz, you should have gotten like 155 some odd million ways of doing this. So any questions about that? So, you know, in this example with the people going out to eat, we had like 8 people, 2 groups of 4, and that led to 70 things. You could actually list them all out and make sure you list them out and don't double list anything and get every single possibility listed and listed exactly once. You can imagine that this would be quite difficult when you need to do 155 million of them. And you also want to make sure that I haven't listed any of them multiple times. So the good news is, rather than worry about generating every single possible sample and generating all of them exactly once, we just generate a lot of them and don't worry about whether we generated all of them or whether we generated some of them multiple times. We're going to get an estimate for the p-value by just generating tons of permutation resamples. But how the resampling process works is we would take these 15, these 30 people that were in this study. So there were 15 men and 15 women. So you group them all together and you just assume, like, let's just assume that gender wasn't really had anything to do with it. It was, we would have gotten the same difference if we just randomly assigned 15 people to one group and 15 people to another group based on randomness and not based on their gender. So how the resampling process would work is, like, we would group all 30 people together and then we randomly pick 15 of them for one group, and then we put the rest of them in the other group. And again, these groups don't have to be the same size. And then each time we generate one of these samples, which is called a permutation resample, then we calculate the difference in the means of those two groups. And then we repeat and we repeat and we repeat, and we do this many, many times. Like 1,000,000 times, 100,000 times, that should suffice. And again, because we're using R to do these simulations, it'll only take R a minute to do like 1,000,000 simulations for this. And once we've done this many, many times, then we can stop, take a look at, here was the sample that we had, where does it fit in with all these other possibilities that might have happened? And then we can see how extreme the value is. So I would definitely encourage you guys to open up R if you don't have it open. And there is actually a R file that's called Hotwings. That's where this code can be found. So this is posted on Canvas. And so the idea is we're going to go through a couple of different types of permutation tests. So this one is going to be on means. We'll see what happens when we do proportions, and we'll see what happens in situations where we don't want to treat our samples independent from each other. So my suggestion is, as we're going through these permutation tests, I wouldn't expect you to come up with this code on your own. We'll kind of go through it together. But once you've seen this code, you should be able to understand what it's doing and then be able to tweak it a little bit to fit the needs of another problem. That's kind of the idea here. So what we want to test is HO was that these differences, there was no difference, and HA is that men were eating more wings than women. So that obviously is not something that R is going to do for us. So here's a nice function. We don't need to do it this way. It has a lot of other applications outside of just this. So this is T apply. Let me just copy this someplace cleaner. So it takes in two inputs and it needs a function. So what this is telling us is, right, we have this data set in resample data called beer wings. One of the variables in that data set is Hotwings. So it might help for you if you're in R, you can do a view beer wings, do a capital V, and that'll show you what the data set looks like. It's not that big. There's 30 people in it, so it's not a crazy data set. So this is just a column of how many wings did each person get. This over here says, okay, let's calculate different values based on gender. So for each gender, we're going to do some calculation of hot wings. And this tells us what calculation to do. So this would say for every variable, so notice this here is a categorical variable. And this over here is a quantitative variable. So it's saying calculate the mean number of hot wings for every category in the variable gender. And so hopefully you can see how you could tweak this to do other things. If you were curious who drank more beer, then change hot wings to beer, right? If you wanted to, analyze it by some other category other than gender, you could put age in there if that was recorded in the data set. We could do other things, and we could do variance, we could do any other calculation besides mean. And so so remember, the first thing that you'd want to do is be sure that you do library resample data. And I'm just going to check the calculation here. And then if you do T, apply beer wings, hot wings. It's better to be talking about beer and hot wings at like 2. When I have this class at 9 a.m., it's not as appetizing. And then you can see it gives you 2 different means, right? So you've got like a female mean and you've got the male mean. So for those that are doing this, the output that I'm getting looks like 9 repeating 3s, 14.533 repeating. This was the mean amount for the females, and that was the mean amount for the males. We could also have subset the data and then calculated the means that way as well, but this does all of that kind of in one shot. So it's a nice command in R. Keep that in mind. Any questions about that? And so this is important because this is going to tell us our test statistic, right? So that's what this observed is over here. So now observed is actually storing the value, which is 14.53333 minus 9.3333, whatever. So this is our test statistic. And notice I've saved it to this thing that I've called observed. And so in this case, what do we get when we take that difference? I don't know. What do we get? Oops. .2, right? I'm slow here. Okay, so our test statistic is 5.2, and that now is being stored in Hotwings. Okay, and so next we want to know is we need to set up the permutation distribution. And then the last step in part C is going to tell us how we calculate the p-value. So this is the key part of the code, definitely right here, is how we set up these permutation distributions. So I want to kind of break down that what's going on in stages here. So this first statement here, we've seen the subset function before. Here we've added an extra command at the end. So what this is going to do, we actually haven't like filtered out anything here. All it's doing is it's going to peel off just the variable Hotwings, and it's going to ignore all of the other variables, but it's going to pull off all of the Hotwing values into one column. And this drop T means it's going to have no header. So rather than be treated as a table, it's going to be read as a vector. So I'll just say these commands are going to work with our data stored in a vector as opposed to a table. So it doesn't like kind of the table structure that it has headers and things like this. We don't want headers. We just want a bunch of values. So if you're looking at that Hotwings data set, that's just going to pull off a vector of 30 values. There's no header. There's no other indicator on these things at all. We don't even know who was what gender in as far as this data set goes. So that's all step one is. So this is kind of, you can think of as pooling all of our people together, right? We're going to ignore who was originally in the male group and who was in the female group. So this is, right, all m plus n values that are in the data set. So any questions on that part? And I would definitely encourage you guys to be very, very thorough about how you read this code, because we're going to be adding layers to these things. So the more comfortable you get with what each of these things are doing, the easier it's going to be to know where to tweak things for the different problems. So kind of this is just setting up our sample, this first step over here. This n is going to tell us how many resamples are we going to do. And ideally, we would get like all 155 some odd million of them and get each of them exactly once, but we're not going to stress about that. Instead, we're just going to generate 10 to the 5th minus 1. We'll see maybe why I put the minus 1 here in a second. We're going to pick a nice round number and then subtract 1 from it. I would say you don't want to go too far below like 1,000 things. I would say the larger you do it, the better it's going to be, but the longer it's going to take R to do it. And this over here, this vector result is going to store like all of the hypothetical differences that we could have in our sample means. So we're going to store 10 to the 5th minus 1 differences between the mean of group 1 and the mean of group 2. And these are going to be means that are just randomly generated as opposed to generated based on gender. So right now, it's just an empty vector where we're going to eventually save our differences. But we need to first create this before we can save things there. So that's all that was going on in step 2. So kind of these first 2 lines of code are really saying, here's where our data is. Here's where we're going to store the fake differences that we generate. And then we begin a for loop. So for anyone that's done programming, you probably have seen these before. If not, then just know that, sorry, that's not what for loops do. It's going to start with, the number 1. It's going to go through this code, and then it's going to pop back up here and then say, now we'll do this a second time, and it's going to repeat this n times. In other words, it's going to do this, 9,999 times. So this is how we are generating our samples. This is the key step here. So I just kind of said, let's say hypothetically, the first, it's going to say, okay, first I equals 1. And what this line of code right here is telling us is it's saying, pick 15 values out of the first 30 integers without replacing the value each time you pick it. So in other words, this is saying, like, who are the 15 people that we're going to assign to the group that's male? And then we're going to send the other 15 people to the group that we're going to consider the female group, although they're just being randomly sent to these groups. So, right, when we do something like this, one possibility is going to be, it's going to pick 15 numbers randomly between 1 and 30 without picking the same thing twice, right? Once a number has been picked, it can't be picked again. So maybe I do this for the first time through that for loop when I is 1, and I get a bunch of values over here. So this is going to tell us that person 3, which is this person right here, right? They've been selected for the male group. And this is telling us person 4, they've also been selected for the male group. And then a bunch of others, and then we're also going to select, person 28 gets selected to the male group. So some of these values are going to be picked in the first group, some aren't going to be picked, and then they're going to be put in the second group. And this is all done randomly with this sample command. This means randomly pick out of this thing, this many things, and you can ask it to do it with replacement or without replacement. You'll see there will be some times where we do want to pick with replacement. Okay, so any questions about that? Okay, so that is the process of like recreating samples. And then this line of the code right here is going to calculate the difference in sample means based on that sample that we just created. So I think this is a little bit clear maybe what's going on, but this is going to create the mean out of all of the hot wing people that were selected. So this thing that's called hot wing index, right? Index were these numbers, and hot wing index is going to be the corresponding amount of wings that each person in this data set had. So if my index has person 3, right, I would say, well, person 3 had 5 wings. Person 4 had 6 wings. And then the 15th person in our data set was person 29, who had 18 wings. And when we say hot wings minus index, it means it's going to pick all of the rest of the hot wing values that weren't in index over into this one. So this is like our 2 groups that we have now. And rather than decide these groups based on the gender, they're being decided just on randomness alone. And then we want to compare, like, what was the spread of all these random samples to the one sample that was based on gender? Does that one sample that was done based on gender seem to fall in to the general scheme of things, or does it seem to be an extreme value? So what happens at this stage is it's going to say, okay, for the first time that we've done this, here were the 15 people, here was the mean amount of hot wings they had, here were the other 15 people. It's going to calculate some difference. Maybe that difference is 6.1, and then it stores it in result. And then it's going to go to N2, N3, and 4, and 5. And it'll do this like 10,000 times. All the way down over here, the last entry would be 10 to the 5th minus 1. That's where that's coming from. So that's like the distribution of differences of sample means that we're getting. So rather than create this thing like theoretically and say, based on the central limit theorem, I kind of know how these things are going to be, what we're doing is we're just saying, based on these simulations, these are the types of differences that we're getting, and where does the difference that we actually observed fall into all of these other random differences. Okay, any questions? Okay, so that is the set up the permutation distribution, and then we've got this vector result, which is really our permutation distribution. It's storing all of these differences. So it's storing the distribution of all these differences. And then we calculate the p-value over here with this command. So what this command is doing, maybe I should pull this out. This is a true false operation in R. So rather than give you a number, it gives you 1 if it's true, and it gives you a 0 if it's false. So keep in mind, you know, we've got result is a vector of all of these differences. Okay, observed was the actual difference that we had of 5.2. So it's going to go through and take a look at all of these differences that you got in your vector result. So maybe result 1 is like 3.5, and result 2 is 8.1. And it's going to compare your simulated difference to the actual one. And if it's a false statement, then it's going to have a 0 over here. And if the statement is true, it has a 1. And then this sum says we'll add up all of these values. So that's exactly counting up how many samples were as or more extreme than observed. So that's what all this stuff is counting over here. And now here's this little subtle thing about why I generated 10 to the 5th minus 1 samples instead of 10 to the 5th. is that there's one sample out there that I know for sure I want in my distribution, which is the sample that we started with, right? So if I do this permutation distribution, I'm certainly not going to get every possible sample out of that process, but I do want to make sure that I include the one sample that I started with, okay, which was set up based on gender. So that's why we add a +1. This is a ratio. So I'm going to add 1 to the numerator, since the sample that we started with is by definition equally extreme to itself. So in the numerator, you're going to have this number of samples as or more extreme. This +1 accounts for the actual sample that we have. And then we divide that by n+1. Okay, we add 1 back now since we included one more additional sample than what we had in our permutation distribution. So now we actually do have, like, in this case, we had 10 to the 5th, we have 10,000 over here. Sorry, 10 to the 5th is 100,000, right? We have 100,000, so I missed a 9. And so this is exactly what the p-value is, right? The number of things that are as or more extreme divided by all of the possibilities. So this is like that 7 out of 70 that we calculated for the diner problem. Any questions about that? That's the kind of full rundown of the code. And let me just see what it does for me. Let me share my R screen with you guys. So here's the Hotwings permutation test. Again, all of these comments in green are commented out. Otherwise, I tried to put some comments in the code that basically we talked about while we were doing this, in case it's nice to have it in the code sometimes when you're working with it. I added a little thing down at the bottom, which is actually going to create a histogram of results. So it's going to plot all of the differences that we got and see where our observed difference fits inside of all of the rest of them. So I added one little part in here. But if you want to run the whole thing, there are different ways that you can do it. I'm just going to highlight everything and click run. And it takes a little while because it's doing like 100,000 samples, but that's how long it takes R to do it, right? And so here you can see the permutation distribution. This line that we have over here, this blue line, is our observed value. We had an observed difference of 5.2, and now we can see that that does seem pretty extreme, right? If we were to just divide people randomly, then we are getting that the differences would be 0. That's what we would expect. So this distribution does fall in line with the null hypothesis, right? That there is no difference between these two groups. And then we observe that our sample is like way out over here. That seems to be beyond the realm of sampling alone, right? There seems to be something more drastic going on in why we observe this difference beyond just how we sampled. So in particular, the p-value we got is over here at 0.00089. So this is saying like there would be a 0.089% chance of getting a sample this crazy if there was no difference in how much wings people ordered based on gender. So basically, we either just picked the most miraculous sample that there could be, or more likely our original assumption might have been wrong. But who knows, right? Sometimes you do pick really bizarre samples and you make a wrong conclusion. That's part of statistics, unfortunately. But you try and control for those things as best you can. Okay, any questions? Yeah, sorry, I missed this question a few minutes ago. There was a question about capital N. It came just to me. It's a good question. So the question was like, why did we pick this? Oh, sorry, forgot you're looking at R. So I got a good question in the chat, which was like, what was special about picking this value of N? And I'll say, hopefully it makes sense why we subtracted 1 at least is because we want to add back our original sample in later. Just know that like you can pick anything you want for this. The larger you pick it, the better your approximation is for the p-value. If you pick it too large, then it might take a whole lot of time to do it. But I mean, we did 100,000 in about like 2 seconds. So you could add some powers of 10 on there. The higher it is, the better it'll be. Well, I'm just going to use 10 to the 5th minus 1 as my convention. That's large enough and can be calculated pretty quickly. That's why I picked that one. But whatever you pick up here, yeah, you definitely want to make sure you use that same value when you calculate your p-value. So really, the only difference between this and the diner problem is that we didn't waste our time trying to list out every possible one exactly once. We just said, just generate a whole bunch of them and let's see what happens. Okay, so let's try and apply this idea to some other problems. So this same data set that we worked with a week or so ago, flight delays, right, that had the American and United flight data, that was a really large data set. So this is dealing with like over 4,000 things in our sample. So here we want to determine, right, is the variance of flights in May different from the variance of flights in June? And so we still don't want to go right into R. We want to make sure we set up our hypotheses. So in this case, right, we would say, as usual for the null hypothesis, is that there is no difference. So in other words, if we state this in terms of population parameters, we're saying the variance for May minus the variance for June is equal to 0. What would the alternative hypothesis be here? Does anyone want to share that?
Would it just be not equal to 0?
That's right. They were not suspecting that May had a bigger variance than June or June had a bigger variance than May. They're just curious as far as whether there's some difference, one bigger than the other. So that would be, there is a difference in the variance by month. So in other words, let me state it like this, sorry. That their difference would not be equal to 0, something positive or something negative. And so, so any questions about the hypotheses? Okay, then let's come over to R. And I would encourage you guys not to open up the the R files that we have for the variance. So there are solutions to this up in R. But maybe let's think about, we've got this thing that we're working with. And let's think about how we can tweak it for this example. So, okay, we've got this data set is in resample data. So what would I want to change about that line of code?
Yeah, you would change the data set that it's coming from. So that would be flight delays.
That's right. So we got.
And then you would change the variables.
Yeah. So what's the?
That would be flight length.
That's right. So this is the category quantitative thing, right? This is some variable that's some number. In this case, it was flight length.
Then the other one would be the airline.
Flight delays, and so we were trying to parse this out by, not by airline, but by. We're trying to say was the variance of this compared to the variance of that, and how were we
by month?
By the month, yeah. I think
By
that
month,
variable
okay.
is called month, maybe. Yes. And what do you think we want to do at the end here?
Would we still do a mean?
So what's the parameter that we're comparing about the flight length?
Oh, variance.
Yeah. So let's see if there's a function for that. And I just started typing VAR, and this tells me, yes, variance, this calculates the variance. So the formula for variance is just VAR. And then if you run this line of code, it'll tell you what these variances down at the bottom, what the two variances are. And then we could do, this tells me how to update my observed difference. And the other one is 1684.43. So now I just ran that. So we could check to make sure that my observed difference got updated, right? From the 5.2 that we had for the wing example, now is this 123. And so now we're going to do the same permutation resample. All of that process is essentially going to be the same, except instead of comparing means, right, we're now going to be comparing variances. So I don't know. I don't want to call this Hotwings. We can call this flight. Maybe not. That's used. We'll call this like flight. That's also used. I'm just going to call it X. That's not used. You can call this whatever you like, as long as it's not something reserved. And what we want to do here is pull off the flight delays data. The variable that we want to select is flight length. And we want to create a vector as opposed to a data frame. So that's why we have that drop equals true thing there. So this is just going to pull off a column vector of 4,000 some odd values that are the flight length of each of those flights in that data set. I don't need to change this. I don't need to change that. But I do need to change this. And now we need to know how many flights were in each of these data sets, right? I need to know how many flights were in May, how many flights were in June. So
Can you just do another T apply?
You could, yeah. I'm trying to see. Yeah, I guess I didn't include that over here. So we could do something like, what we need to do is count up like how many total observations are there. So for that, I could do like view flight length, flight delays, excuse me. And that tells me, okay, this is the 4,029 entries that we have over here. So that's good to know. And now we need to be a little bit careful about things. So first of all, we're going to use variance instead of mean. And I call this thing X instead of Hotwings. But want to be consistent with how I do the difference up here, like the ordering in terms of whether I did May minus June versus June minus May. So the way that I did it, right, I did the 1,880 or 1,808, which was May. So I did May minus June. So when I come down and do these calculations, this first thing should be like my fake May, and this next one should be my fake June. And here, what I want to just be sure we're careful about is these two sample sizes are not the same. So it's not like I'm breaking it in half. I have 4,029 flights. And we're going to let M be the number in May, since that came first. We did May, and N is going to be the number in June. And so what I would like to do is count up how many flights were there in May versus June. And, you know, we could do like a table on that, right? We've done that before, which is going to count. That will tell me how many are in each one. So I've got 1,999 in May. So that's what I'm going to pick for my size. Right? So that size should be equivalent to how large, how many things were in this group over here. And then the rest of them are going to go over here. So that's a really important thing. I will say, like, when I go over people's code, that's often the thing that'll be kind of missed, is like, what's the significance of this size? So this size, again, should equal the number of things in May. So this is going to pick, 1,999 of these values, say that this is now May, this is our random May, the rest of them are going to be June, and then let's calculate the variance of those, calculate the difference of those variances, and then go through all of this. I don't need that stuff. This is what I need. So I'm going to execute this, but not quite the p-value just yet. So any questions about those tweaks that we made? Well, that does not look good. What happened here? Let's see. Yeah, looks okay. happened there? Maybe I want to do one of these. This is not what I'm asking it to do. Oh, I see. This was I mess up my code sometimes on purpose. There's no such function as variance. It's VAR. Thank you. Yeah, sorry. I did it right up here. When
I almost asked about that earlier because I
Please do.
know you first did var and then you did variance.
Yeah, thank you. I was thinking that maybe I need to call this something different, but I don't think that's the problem. I think this was my problem. Yeah. So let's try this all again. And hopefully we get something that looks more like we expected. It's running. So when you see this little stop sign over here, that means it's still running. Still running. There we go. Okay, that looks better. So now you can see how long it takes. So variance is a longer calculation than mean. That actually took like 30 seconds as opposed to 2 seconds. And now we can see, like, here was the variance, that the difference of the variances that we observed, and now we can see that it's not as unlikely as like the beer wing example over there. And so now when I consider something as or more extreme, since we didn't care whether June was bigger than May's variance or vice versa, I'm going to consider anything over there. Let's see if I can do this. Yeah, okay, so good. So I would want to put a little red bar, I don't know if you saw that, on the left, and now I'm going to consider extreme stuff to be anything that is below the line in red or above the line in blue. And because these things are symmetric, right, what I can do is calculate what's the area above the blue line and multiply that by 2, right? Because that's going to be the same as the area above the blue line and the area below the red line. So when you have a two-tailed test, a couple things to worry about. And that is, sometimes we have an alternative hypothesis if we have a less than in it. Then we would think things that are more extreme should be even further below. So you might need to change this inequality sign. You will have to change these inequality signs depending on your alternative question. So just keep in mind, this last line of the code is not going to be the same always. It's going to depend on whether your alternative has less than, a greater than, or not equal to. And since we have a two-tailed test here where our observed difference was positive, we're going to keep this bigger than. So we're going to calculate what this line is doing here is it's calculating how much area is above the blue line, how many samples were above the blue line, and then multiply it by 2 to double it and include the stuff over here. So in this case, the p-value is the last thing. I'm getting a p-value of 0.06922. If you're running this code, you probably got something different, but it shouldn't be drastically different because there is simulation going on here. We're all not going to get the same exact answers, but I shouldn't get this and you get like 72%, right? They should all be within pretty close realm of each other. Okay, any questions about that? So all of that is in its own file, flight delay variance, which kind of goes through exactly what we just did here. I don't think I have the line for the p-value over here, however. This just created the distribution. So you would need to add the code for the p-value for this part. Any questions?
It's pretty cool to see like a full script like that.
Sorry?
I was just saying it's pretty cool to see a
Yeah.
full script like that. I'm more sold on R now.
Yeah. And I'll just say, you know, for anyone that's programmed in other languages like Python and whatever else, it's essentially the same. I mean, the syntax, you know, this uses a comma, that uses a semicolon. Like the syntax might be a little bit different. The commands might be a little bit different, but like a for loop is a for loop in any language. It's pretty much, the logic is the same. Yeah. So it's more or less the syntax that you might need to adjust. Yeah, and that's why you definitely want to be doing those things in scripts as opposed to like line by line by line. Okay, and so a couple of other things. So if we wanted to do something about is the proportion of times flights were delayed more than 20 minutes different from the proportion of times flights were delayed more than 20 minutes in June. Right, so now we're comparing proportions. So we'll let like P denote the proportion of all flights delayed more than 20 minutes in May, June. We're going to assume there is no difference. And over here for the alternative, what inequalities should we have based on this test?
It just says we're delayed more than for each, and they're just different from each month. So it'd just be not equal again?
That's right. Yeah, there's a lot of words going on here. That's right. So so this is what we're calling like P-May. So right, there's like a whole bunch of flights. Some of them were delayed for more than 20 minutes, some less than 20 minutes. And there is a variable in the data set called delay, which measures that exactly as a categorical thing, as opposed to saying like, how long was the delay? I think it's just a yes or a no, right? Was it delayed for more than 20 minutes? And so we're trying to compare these two proportions. And the question is, are they different from each other? Not was May more delayed than June or something like that. Okay, and so here's the R code for the data set for the R file called flight delay prop test. I have it over here. Okay, so yeah, you guys are looking at my iPad. Yeah, sometimes I forget what screen you're looking at. So here's another way. We've been using subset to create like our vectors. If you just do this, this creates a vector called delay, which just has the delay time. So there's other ways that we can do these things. Just want to point that out. But here's a case where, and you know, tapply can't really work to this because tapply works better with numerical data, right? Here we have two categorical things. We have month and we have, was it delayed more than 20 minutes, yes or no? So tapply isn't going to work here. So what I did is I created one vector that has delay times for just May. So it's going to look like that. It's just going to be some vector of yeses and nos, but it's a really long one because there were like 2,000 things in May. And then we do the same thing in June. So this is saying pick off just the variable delay for just the month of June. Oh, I'm sorry, it was variable delay, anyone has R open, can't remember, there's so many variables in there. Is delay categorical or is that numeric?
I don't have this one open right now.
So delay is actually a numeric value. I'm looking at it right now. So it's telling you like how many minutes was this thing delayed, sorry. So this is not going to be yes or no's at first. It's going to be like how long was the flight delayed? So these are numbers, sorry. And this does the same for all of June. And this is going to work similar to how we calculated p-values. So remember, these inequalities are true false statements. So this is going to go into the vector for June, for example, and it's going to look at each value in the vector. And if it's bigger than 1, it's going to give us a truth value of 1. And if it's less than 20 or less than or equal to 20, it's going to give us a truth value of 0. So it's going to look at each of these values and say, is it bigger than 20? And if it's not, it gets a 0. And if it is, it gets a 1. So this now becomes a vector of a bunch of zeros and ones. And if we take the average of all of these zeros and ones, it's equivalent to counting what proportion of entries had a delay longer than 20 minutes. So that's telling us what p hat for June is, for example. So this line of code is calculating the delay for June and then subtracting the delay for May. So we had to do a little bit of work to get that. There wasn't any built-in function like variance or mean that says, is it bigger than 20, right? So we had to do a little bit of calculation on our own for that. And now the rest of this stuff should look pretty familiar, or starting to at least. So here's the number of samples that we have. Here's where we're going to store our permutation resamples. And then we're going to do our for loop. Again, this is because this is how many values were in the sample to begin with. And because I did my observed, in this case, as June minus May, I'm going to want to compare differences that have the same thing, right? So the way that I set up my observed sample should be consistent with the way I calculate these differences. So this is what we were talking about last time. So if my first thing is June, then this number over here should correspond to the number of June observations. And as far as these differences go, it doesn't matter whether you do June minus May or May minus June. You just need to be, however you decide to do it up here, it needs to be the same down here is all. So this is going to pick, 2030 to be our like replacement for June. And then for those 2030 things that it picks, right, it's going to go back into the data set that we had way up over here, which was all of the data combined for May and June. It's going to pick off a bunch of them and assign them to like the first sample and say what proportion of these things were delayed for more than 20 minutes. All of the rest of them go over here. And so now this is calculating the difference in these two proportions. So this result is giving us a whole distribution of different ways that things could have been sent to June and May. And down here, we do the p-value, where again, we put a 2 here because it's two-tailed. And we use a greater than or equal to because our observed difference was positive. If our observed difference was negative, then we'd want to say, what are things that are less than it, and then double that. So keep that in mind. There's two things that you might want to adjust with your p-value, and that's those two things there. Okay. So I won't kind of run through the code right now. But if you did run it, I was getting, or at least when I've done it in the past, p-value here is approximately 0.01694. Okay, any questions? Okay, well, that's good, I guess. Okay, so maybe just to leave us with something to think about, and we can kind of pick up from this point. But the examples that we've been doing have been two independent samples, right? So we have flights in May, flights in June. You're either in May or you're in June, right? You can't be in both of them, and there's really not such a natural way to match them up. If we were trying to answer the following questions, so a bunch of years ago they came out with these newer swimsuits that some athletes were using in the Olympics and others weren't, and they were suspicious that maybe these swimsuits were giving an unfair competitive advantage. So they did a study where they wanted to see whether these swimsuits actually do help people swim faster. And so they took 12 swimmers. Okay, when it says no wetsuit, I don't think that means I think they were wearing something, just not like the fancy wetsuit. They were just wearing like a regular bathing suit. And so here's their maximum velocity with the wetsuit compared to their maximum velocity in terms of meters per second with a regular bathing suit. As you can see, okay, this first swimmer, their maximum velocity was a little bit bigger with the swimsuit on than without it. And so was this person's, and this person, and this person, and this person. So we have 12 swimmers, and now you can think of, here's one sample of people not wearing, or people wearing the wetsuit, and here's another sample of people that were just wearing a regular bathing suit. So let's just leave it with a question here. see how we would set up these hypotheses. So there's a poll open for that. All right, sorry, I've muted myself. So, all right, so here are the results. Let me share them with you. So the null hypothesis, right, is going to be that there's no difference. So when we state these null hypothesis, we're comparing two groups. It's very simply going to be there is no difference. And HA, now we want to consider like whether there's some direction implied in this. And so we're pretty split here in terms of it doesn't make a difference or it helps people swim faster. And since they were suspicious that this would help people swim faster, then that should be the alternative hypothesis, if that's what they want to show. Does that make sense for those that might have said that it does make a difference would be kind of what they wanted to see if they were suspicious that whether the wetsuit made a difference one way or the other. But because they particularly want to know, does it help them go faster? If it slows them down, then fine, you're welcome to wear it in the Olympics, right? But what we want to know is it going to help you swim faster?
So on the poll results, are the blue is the correct answer?
There is no way for me to put in correct answers here. So I think it's just red is the most common one and blue is the others. And we had a tie,
okay.
so that's why two of them are red. Yeah.
Yeah, I see.
Yeah, so so the swimsuit helps people swim faster would be the alternative in this case. Yeah. And what do you think would make sense as a observed test statistic here? We've got this data set. Like, what are you looking at in this data set if you're considering whether or not it made a difference?
The difference of means?
So in the sense of the mean velocity for the wetsuit minus the mean for, we'll call that control.
Mm-hmm.
So that's kind of right, and also not quite right. So I think like mathematically this will come out to equivalent to what we might want to think about. But what I leave you guys with considering is we don't want to do the same permutation resampling that we've done in the other cases. So for example, I wouldn't want to take, all of these values, let me put it like that, and say, okay, we have 24 values over here. 12 of them were in the wetsuit, 12 of them were in the regular bathing suit. And we wouldn't want to just say, let's randomly pick some values. So let me randomly pick this one, and this one, and this one, and this one, and that 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 one. And that's going to be my wetsuit group, and put the other ones in the non-wetsuit group. We need to be a little bit more careful about how we split these up. So yeah, we're out of time here. So I'm sure you're anxious and on the edge of your seat, but I apologize. We'll just have to wait until Monday to see how we're going to do this. So I will, we'll pick up with this one. I want to talk about this one together rather than put this in as a quiz. So this is kind of the last bit that we'll talk about in chapter 3, and then we'll start talking about sampling distributions in chapter 4. So you'll have a reading quiz. I'll get that up sometime tomorrow, Friday. That'll kind of get us going in chapter 4, but we'll start off class on Monday with this example before we move into chapter 4. Okay, well, have a nice weekend, everybody.